Welcome back, children. I'm going to continue from where we left off in the last class. In the last class, we talked about the force experienced by a moving charge in a magnetic field. We said that it is given by this equation. F is equal to Q V cross B, where Q is the amount of charge on that charge and V is the velocity of that charge and B is the magnetic field in which this charge is moving. It is always V cross B. It is never B cross V. We have to be careful about the order in which V and B appear in this equation. If we change the order, instead of V cross B, if we say B cross B, then we will get the opposite direction. It is V, if it is B, V cross B will give you the upward direction, but B cross B will give you the downward direction. You know from mathematics that this order is important. Then how do you ensure that you don't confuse, you don't forget this order? I would ask you to remember Queen Victoria Building. Queen Victoria Building. So QV cross B. So there is no way you can confuse this with V cross B. Or B cross B with V cross B. So it is always V cross B. So remember this Queen Victoria Building. So there will be no confusion at all as far as this expression is concerned. Okay. So what it tells you, let me explain once again. But let me take this blue as a direction of the magnetic field and this black as the direction of the velocity vector of B. Okay. Let's say the magnetic field is acting in this direction. Let's say like it's going into the board, and at this point, okay, this is B is going into the board at this point, and you have the velocity of this charge. Okay, the velocity vector of this charge, the charge at this point is moving in this direction, let's say this vertical direction. And notice that the angle between B, which is the magnetic field, and V, the velocity, it is 90 degrees. The angle between the two vectors is 90 degrees. So, if the angle between the two vectors is 90 degrees, I am just going to make some adjustments because it's difficult for me to call them. So, I hope you understand that they are at the same point, not at two different points. At the same point, B is going into the board and V is going up. In that case, the force will have this directions because V cross B will give you this direction. So the force will be in this direction. Red is the direction of the force. So notice here that velocity and the magnetic field are perpendicular to each other, and the force vector at that point would be perpendicular to both of them. So let me illustrate that on the board. So this is my magnetic field. It's going into the board. Suppose a charge Q enters this magnetic field in this direction. Suppose magnetic field is in this direction, it's going into the board. Now the charge is moving upwards, like that. So the charge is moving like this. This is the velocity of the charge. Then what happens is that this charge Q will experience a force in this direction. Okay, so let me say this is Q is a charge and this is the force. Is direction of the force. And blue, that's B. B vector is into it. So this force is actually V cross B. That. Because the force direction is going to be this way. Okay. So now what will happen to this charge if this is in this direction? It is moving with this velocity. The force is pulling it this way, so it will bend. Okay, it will bend. But as it bends, does the angle between B and V change? It doesn't. There is no here. This is B and this is V. As it bends, you notice this angle, the angle between V and B does not change at all. Here, as you see here, it can change. But as you see here, it is always 90 degrees. The angle between B and V is always 90 degrees, even if V changes this way. So then what happens is that as it turns, then F will be in this way. Suppose if it is like this, so instead of V being like this, if it is turned like that, okay, then force would be 90 degrees to both of them. You see, note that the force direction changes now. Previously when it was like this, then the force was, when it was like this, vertical, then the force was like this. But as it turns like that, same 90 degrees, but as you see from here, there is an angle, but this is 90 degrees between these two. Then this should be like this. So it is like this. As it turns, then notice it, the F changes. F changes its direction. So as the body or as a charge moves like this, then the force is changing its direction because the velocity is changing. Because the force is acting on it, the velocity is changing. Since the velocity is changing, then the force also changes its direction, and finally it will make a circle around this. It will be centered, and then this charge, even though it enters this magnetic field vertically, and because of this force, then it will bend. This force changes the velocity. Force must change the velocity. So it changes the velocity. As it changes the velocity, when I say it changes the velocity, it does not change the magnitude of the velocity. Because notice that F is acting perpendicular to the direction of motion. If a force acts perpendicular to the direction of motion, it is not going to change the speed, it will only change the, it will not change the speed, it will only change the direction. So it changes the direction here. So the body, the charge goes around it like this. So it makes a circle. Okay, if it makes a circle, then what happens? Obviously the circle, like a planet, you see, like a planet moving around the sun. So there is a central place, and then there is a force which is pulling it towards the center. That's a centripetal force, and it goes around it. Okay. So now, what is the force acting on it? The force acting on it is equal to Q V B. Sin theta is sin 90, which is 1. The direction of the force is changing all the time. So I'm not going to consider direction now. But this is the magnitude of the force. Okay, this is the magnitude of the centripetal force. The centripetal force will change direction continuously, but that doesn't matter. No, we just want to take the magnitude of the force. So go to QVB. Sin theta is 1 now. Okay. And since the force is acting on a body, then it should have an acceleration. It will have a centripetal acceleration now. The centripetal acceleration is given by the formula v squared by r. So the force, this force which is acting on this body, must produce an effect, and that is equal to ma. F, the force, will produce an effect of ma. So this is going to be equal to ma, which is the centripetal acceleration. This acceleration must be in the same direction as the direction of the force. Okay. So QVB now is equal to m is can be written as v squared by r. Then r can be written as, okay, v and v will cancel. R can be written as mv by qv. So the radius of the circle the charge makes depends on the mass, on the charge value, and the speed with which it is moving, and then the B value, the magnetic field value there. So if the charge is more, then radius will be smaller, and if the field value is more, then also the radius will be smaller, because the force will be more in this case. As the force is more, then clearly the acceleration will be more. So the radius could be smaller, and mv by qv. So this is the equation which gives you that value. So if a charge enters a magnetic field in a direction perpendicular to it, then we know that it is going to make a circle. If it's a positive charge, then it will make a circle like this. If it's a negative charge, then clearly it will make a circle like that. Okay. So if it is a positive charge, then it will make an anti-clockwise rotation. If it is a negative charge, then it will make a clockwise rotation. If it is perpendicular to if the velocity of the charge is perpendicular to the magnetic field. Okay. But what happens if the velocity is not perpendicular to the magnetic field, but then it has some angle here? So it has an angle which is less than 90 degrees. Then what is going to happen now? Well, if this is the case, then clearly I will have two components to it. One is the component along this. I can resolve this basically. I can resolve this vector, this v vector. Let me try to hold it properly. So let's say if this is a v vector, this is the b vector, so they have an angle between them which is not 90 degrees, then actually I can resolve this vector. It will have a vertical component and also a horizontal component. The vertical component clearly will make a circle as we just saw. But what about the horizontal component? The horizontal component will not experience any force. So what I mean by that is, instead of moving vertically, if the charge moves along with the magnetic field, if both of them are aligned, if their V and B are parallel to each other, then there will be no force because it's V cross B. So this component, this horizontal component, will not experience a force at all. So this velocity will not be affected. This velocity will be affected because there is a force acting on the charge, and it is trying to pull it to the center. There is a centripetal force. So that is why it is trying to make a circle. So this component will be affected by the magnetic field, the vertical component. But the horizontal component will not be affected by the magnetic field. It will go untouched. So now what do you see here? You see two things. One, the vertical component will make the charge to make a circle, and the horizontal component will just go unchanged. So the particle will have both these velocities. The velocity which is affected by this force and the velocity which is not affected by the force. The velocity that is affected by it makes a circle, and the velocity which is not affected by it goes unchanged. So then what happens is that you will make a circle and then you will also proceed in this direction. So you will have a helical path. You will make a circle and then you will go here, and then you will go here, and go here. So the horizontal component, the component which is parallel to the magnetic field, will take it along the magnetic field, but then the vertical component will make a circle. So you will effectively have a helical path. So let's do it now. So there is B again. Let's say like there is B in this direction, and there is V in this direction. Okay, that's an angle theta which is not 90 degrees. So then clearly I'll have two components, or do this way. Okay, I'll have a vertical component and also a horizontal component. So this, I'll say this is the perpendicular component and this is the parallel component. This component is perpendicular to this, to the magnetic field, and this is parallel to it. So this will make the charge to make a circle, and this will push it this way. So it will keep making circles and then it will go like that. So clearly, then what happens is that the body will go like this. So we just saw what would be the radius of this circle. Okay, we just saw that the radius was okay, we said F was V perpendicular QVB, okay, was equal to M V perpendicular square by R. So this and this will cancel. So clearly R was equal to M V perpendicular by Q B. So that was the radius. Okay. That is it. Then what is the angular frequency? So what is the frequency? What is the time does it take to go around this circle? So that can be found. Okay, first let me not worry about angular frequency, let me talk about frequency. Okay, how do you find the frequency? What is frequency? To find the frequency, we need the time period of revolution, right? So what is the time it takes? Time it takes is distance by speed. So I'll call this as. So what is the distance? It takes is 2 pi r. It's 2 pi r is the distance divided by v perpendicular. So that will give me the time it takes to make one circle. Then what is frequency? The frequency is actually equal to 1 by t, and that's going to be v perpendicular divided by 2 pi r. Then what is angular frequency? The angular frequency omega is actually 2 pi to f, so that would be 2 pi v perpendicular by 2 pi r. 2 and pi will cancel, so I will get v perpendicular divided by r. So this is what it is. Okay, that is fantastic. Okay, so omega is equal to v perpendicular by r. So it takes about this time 2 pi r by v perpendicular to make this round. Okay, now it starts here and then it comes back. Okay, then it is where it's back here. Then it goes like this. So you see, this distance between one circle and the other circle is called as the pitch. We call this as pitch of the helical path. If the path is actually helical, the path is helical, and then this is actually the pitch of the helical path. That is the distance between one circle and the other circle. Okay, or the time it takes to finish, or rather like the, yeah, it's the distance between this circle and that circle, if you will put it that way. Okay. So then how do you calculate the pitch now? If we need to calculate the pitch, I know t. T is the time it takes to go from here to here. So that's the pitch. I know the pitch. Now I know the time. And then the pitch is this distance. And how do I calculate the distance? I need to take the parallel component of the speed, and if I multiply that with time, then I get this pitch. So the pitch P is equal to, what is the distance? Is the distance is like, what is the velocity speed? It's v parallel multiplied by the time. So that would be v parallel into 2 pi r by v perpendicular. But what is r? R is here, m v perpendicular. So v parallel into 2 pi into m v perpendicular, so divided by q b to v perpendicular. So this and this cancels. So that gives you 2 pi m q b to be parallel. So that's the distance. That's the pitch distance. Hope this clear to you. Okay. Now we shall do the example problem 4.3. So what does it say? It says, what is the radius of the path of an electron whose mass is 9 into 10 power minus 31 kg and the charge is 1.6 into 10 power minus 19 coulomb, moving at a speed of 3 into 10 to the power 7 meter per second in a magnetic field of 6 into 10 to the power minus 4 Tesla perpendicular to it. What is its frequency? And calculate its energy in kilo electron volts. Okay? It's a very easy problem. It's straightforward application of the formulas basically. The first part is this. They want you to find the radius. So this is what they want you to find. We have just derived that the radius of the circle that the charged particle makes, okay, is given by this expression R is equal to, okay, mv, this is perpendicular, by qb. So this is a perpendicular component of the velocity vector. There is the speed is 3 into 10 power 7 and it is perpendicular to the field anyway. So there is no parallel component. So all this speed would be the perpendicular component of the velocity. So you get here mass is 9 into 10 to the power minus 31 multiplied by the speed, the perpendicular speed in the perpendicular direction is same, 3 into 10 power 7, 3 into 10 to the power 7, so divided by Q is 1.6 into 10 to the power minus 19, and then B is 6 into 10 to the power minus 4 Tesla. So if I manipulate the numbers, then I'm going to get R value to be equal to 26 centimeters. Okay. So the next part is finding the frequency. What is its frequency? Frequency is given by this equation V, again perpendicular, right? So divided by 2 pi r. 2 pi r. There is only one velocity here, that's the perpendicular velocity. So I will just take this as 3 to the power 7. 3 into 10 power 7 is divided by 2 into pi into 26 to 10 to the power minus 2 meters. So if I do this, I'm going to get 2 megahertz. 2 into 10 to the power 6 hertz. So that's going to be equal to 2 megahertz. And the third is a kinetic energy in kilo electron volts. Okay, what is kinetic energy? So K E, kinetic energy is equal to half m v squared. So note that I am not putting any perpendicular component to this because all the speed, whether it is acting in the horizontal component or the vertical component, will contribute to the total kinetic energy. So F mv square will be F into m, it's 9 into 10 to the power minus 31 multiplied by V is 3 into 10 to the power 7, the whole square. So this will give you energy in joules. And then how do you convert that into electron volts? Then you divide that with 1.6 into 10 to the power minus 19, then finally, like you get the value, it's going to be 2.5 kilo electron volt. So that's about it. So this is a very simple problem, very straightforward application of the formulas. We derived the formulas before this and simply apply the formula to the problem, plug in the numbers and manipulate those numbers, then you will get this answer. The one thing that you need to understand is that this magnetic force which is acting on the charge, it does not change the kinetic energy of the charge. Why? The force does not change the speed. It changes the velocity, but doesn't change the speed. Why? Because the body is moving in this direction and the force is acting perpendicular to it. In this case, what it will do is that it will only change the direction of the velocity. It won't change, it won't increase the velocity. So if it doesn't increase the velocity, then it can't increase the speed, clearly. Because velocity is nothing but speed and direction. So if this force, since it is acting perpendicular to the motion, it cannot increase the velocity. If it doesn't increase the velocity, the speed doesn't increase, and when the speed doesn't increase, then clearly the kinetic energy will not change. So the magnetic field acting on a moving charge can only change the direction of velocity, but it cannot increase the velocity or decrease the velocity. If it cannot increase or decrease the velocity, the kinetic energy of the charge does not change. Hope this is clear to you. If you have any questions, let me know, then I'll try to explain these concepts again in greater detail if required.